Okay. Good morning, everyone. Okay, so let me check your attendance. 이재혁 씨, 고하늘 씨, 심준호 씨, 이승빈 씨, 이정태 씨. If you are here, please leave your message. 네, 고하늘 씨 안녕하세요. 심준호 씨 안녕하세요. 이승빈 씨 안녕하세요. 이정태 씨 안녕하세요. 네, 이재혁 씨 안녕하세요. Okay, let's go to the next page. 이충하 씨, 정상아 씨, 홍주표 씨. 네, 이충하 씨 안녕하세요. 홍주표 씨 안녕하세요. 네, okay, let's go to the third page. 김민선 씨, 김유신 씨, 배민현 씨, 배서령 씨, 서하연 씨. Please leave your message. 네, 김민선 씨 안녕하세요. 김유신 씨 안녕하세요. 배민현 씨 안녕하세요. 배서련 씨 안녕하세요. 서하연 씨 안녕하세요. Okay, let's go to the last page. 조대현 씨, 최승규 씨, 김성수 씨, Mr. 나단 마니큐어르. So if you are here, then please leave your message. 조대현 씨 안녕하세요. Hi, good morning, 나단. 최승규 씨 안녕하세요. Okay, then let me check again for missing students. 정상아 씨, and 김성수 씨. So if you are here, then please leave your message. And if you come later, then please leave your message when you come. Then I will check your late attendance. Okay. So good morning, everyone. How was your weekend? And how was your homework number 5? So I hope that everybody has submitted your homework. But if you have any question on homework number 5, then could you please leave your message? Then I can answer your question. So the problem 1 and 2, there were 2 problems, and the first one was calculate the density of silicon atoms, and the answer is around 10 to the 22 per cubic centimeter. And second one is around, that is around 1 times 10 to the 10 per cubic centimeter. So if you have any question on these problems, then please let me know. And even not right now, but if you have additional question during the lecture, then please interrupt me anytime. You are encouraged to interrupt me with your questions. Okay, so any question from students? So if not, then I can proceed with today's lecture content. Okay. So now let's come back to our previous lecture. So you remember that we are now talking about how can we fabricate certain circuit elements in our semiconductor wafer. So if we just okay, so Mr. Sung-Soo Kim, okay, you are a little late, and okay, so I will I will I will solve the problem one. Okay, thank you for your response. Okay, so but just before solving the problem number one, let's make a smooth transition from our previous lecture contents and problem number one. Okay, I will solve it soon after. So in the previous lecture, we have talked about how can you fabricate a circuit element on a silicon wafer. So that was our previous lecture contents, and yes, there is a certain thin silicon wafer. However, we are currently using even thinner part just close by it, can say here, top surface. We just use a few micrometer thick layer, which is close to the top surface. Of course, in order to uh, be connected to other elements, like say that here we have certain voltage source, and in order to connect our device, our circuit element with this voltage source, we have to provide a certain metal line, and there is some part or some port to connect our circuit element and voltage source. And internally, there is a metal line. Yes, there is metal line running over our circuit elements. So this is a scale of centimeter or millimeter scale, and this is a scale of micrometer. So please don't be confused with my drawing. So my drawing is not fully scaled. And now we provide certain part here. However, this one is regarded as a really good conductor, so we don't consider any voltage drop across this metal line. So the point is, all of our interesting behavior should appear in this narrow region. If you remember correctly, the reason why we do not consider this part, this part, this part is basically this part is too highly resistive, and no current conduction is allowed through deep substrate. So now we can think about how can we change or control the conductivity, or in other words resistivity of this part. So this part is just a silicon resin, and how can we modulate the conductivity of silicon? So you know that here we have also silicon, and this silicon is quite highly resistive. So highly resistive. So our goal is without changing the material, so we just introduce less resistive part on this layer. Okay, so now let's come back to the problem one solution. So in order to answer the question of how can you modulate the conductivity or resistivity of this silicon material, first of all, we have to understand the crystal structure of silicon. So let's come back to So I hope that everybody now solve the problem quite easily. So the answer is 5 times 10 to the 22 per cubic centimeter. However, in order to solve this one, we have to, although I gave you a hint for this problem, we have to calculate two different quantities. So two quantities is first we have to understand the crystal structure of our system, and if we know the crystal structure of silicon, then we immediately find that it can be regarded as a cubic structure. So cubic structure means that the cell is a cube. So here we have a certain length scale A and certain length scale A and certain length scale A. In our silicon wafer, this cube is used as a basic building block of repetition. So if we have this cube whose volume is given by cube over A, then we can just copy and paste this way, x directional way, y directional way, and z directional way. Then we will build really a silicon wafer. So volume is given by cube over A and happen to be in a silicon material. In the silicon material, we know that A is close to 5.33 or 43 angstrom. So angstrom is just 0.1 nanometer. So it is given by 0.4543 nanometer. Then you can easily calculate a volume. So Mr. Kim, so are you with me with my explanation? I think that it is not that difficult to calculate the volume itself. The real problem is then in this cube, how many silicon atoms in a cube? So if we know this number, then our solution will be this number, the answer of our second question divided by our volume. So volume is given by cube of 3. Then that will be, this guy will be just a unitless, just a number 1, 2, 3, 4, something like that, without any typical dimension. And here we will have a volume unit. So we will have cube over centimeter. So if we just evaluate this division, then we will have a quantity which has the number divided by certain volume scale. So we will have this quantity, and that answer will be 5 times 10 to the 22. Then problem is how many silicon atoms in our silicon material. That is the main question we have to answer. So think about this one. Silicon's crystal structure can be called as diamond structure. So that is the typical name we call, and let me just draw the position where silicon atoms are found. So I'm just drawing our cube once again, and yes, and let's say this one is corresponding to 0.0.0. So Mr. Kim and our other students, are you all with me? if you don't understand my explanation or my solution procedure, then please interrupt me. It's all for you, so please. And the coordinate will be, in this case, 8, comma 0, 0. And this part will be, of course, 0, comma 8, comma 0. And this guy will have also something like this, 0, comma 0, comma a. So this is the coordinate system. You know that we have length A along the x-axis, the y-axis, and z-axis. And now let's play or let's just place our silicon atoms. So if you don't understand, please let me know. So in this diamond structure, first of all, we just place our silicon atoms at the corner points of this cube. Yes. So now you understand, in this unit cube, we can find 8 silicon atoms at corners. So there are, how can I say, there are yes, there are points which where yes, there are corner points, so you can find 8 silicon atoms. And the typical way to consider the silicon structure is now not only this corner point, but also we can place more silicon atoms. Where? So where can you introduce more silicon atoms? That is given by this way. Here we can find sorry about that. So we can think about 6 faces. So although I have just drawn 3 faces which can be visible, however, you can easily understand there are 3 other surfaces or faces which is not directly visible to us. Of course, if we consider the center point of each, how can I say, each face, then for example, this guy, this guy will have a coordinate like halfway and 0, comma halfway. So are you with me? So simply speaking, there will be something like this: 8 times half, 0, or 0, comma 1. So let me just draw them. For example, if we have half and half for x and y, then we have to place our silicon atom for this lower face, so which is laid on the bottom of this cube. And for example, if we have to consider this guy, then x and z, then x and z is corresponding to this front surface. Then you can also consider other like for example 0, comma half and half, which is given by, how can I say, x, y, yes. Then this is corresponding to this guy. This guy is placed in the left side face. So you can think 3 different faces, and if you change just this 0 to 1 and 0 to 1 and 0 to 1. Also you have corresponding pair placed here and here and there. Okay, so now you understand previously we can have 8 corner silicon atoms, and now we can have 6 silicon atoms at how can I say, faces, or the center of faces. So face centers, so center point of this face. Okay, so if you don't understand my explanation, then please let me know anytime. So now you can think that, oh, this silicon has 14 silicon atoms in its cube. But please, there is one final step we have to consider. Now we can think about 14 silicon atoms, a set of points, and this is usually called as these 14 silicon atoms, or the structure made of this 14 silicon, any kind of atoms, is face centered cubic. So when you say simply face centered cubic, it means that the structure has atoms which is placed at each corner point and each face center point. Then, what is the relation between this face centered cubic and diamond structure? It is like this. First, just to generate a face centered cubic. Then please Ctrl C, copy, and copy and move it. So how many distance? What is the displacement? Then the displacement is just given by 8 times a quarter, a quarter, a quarter. So can you visualize it? So let me just think about this one. If we start from this atom, which was previously located at the origin 0, 0, 0, then that will be moved into a point whose position is quarter A, and quarter A. So where is it? So we can think that a quarter point, and quarter point, and there will be really a small cube generated with this coordinate, and we will move our original point to this point. Then think about this one. Simply speaking, 0, 0, 0 will be moved to cube A, and think about this one. Also, we have previously, for example, we can have A, 0, half A. Then what will happen to this guy? This guy will be just move to this position. Yes, you can easily understand if you have a certain point in face-centered cubic, then just add a vector like diagonal vector. Yes. So corresponding to the diagonal of our cube, then you will have a new point, and at that point or at those points you will have another copy of your silicon atoms. That is called as, diamond structure. So simply speaking, what is the diamond structure? Diamond structure is a set of two copies of face-centered cubic structure, and their displacement is given by this quantity, a quarter of diagonal of our original cube. And natural question is, what is face-centered cubic? So face-centered cubic means that the atoms are occupying the center of the corner points and simultaneously also occupying the face-centered points. Okay, so Mr. Sung-Soo Kim, I think that it will be a little bit lengthy answer, but we are almost there. So you guys, do you understand the diamond structure? Or if you have any question related with my explanation, then please let me know. Okay, so Mr. Sung-Soo Kim, please respond to my question whether you have understood my explanation up to now. So it's not the end of our all my solution procedure, but please leave your message like you have understood them all or additional question. And it is also holds for other students. If you have any question during my explanation, then please let me know. Okay, great, Mr. Kim. And how about other students? So if you are all satisfied with my explanation, then I can safely go to the next part. So so now you can understand face-centered cubic. We can find 14 points in a unit cube, and this diamond structure is just a copy and pasted version of a face-centered cubic structure. So 14 points will be copied with 14 points. So if you are too naive, then maybe you can say that, okay, for unit cell we can find 28 points. Oh, so the answer will be by 28 divided by our volume. But unfortunately, this is not the correct answer. Why? Why we are doing wrong in this procedure? For example, think about our corner points. Yes, there are 8 corner points, but each corner point atom is not fully belonging to this single cube. Think about an atom placed at the origin. If we have an atom placed at the origin, then that is corresponding to this this one. Yes, let's think about this one. But there are 8 cubes sharing this one single atom. So when you count them, actually this guy is not counted as a full atom because that is shared by 8 different cubes. So we have to introduce a weighting factor, just 1 over 8, eighth 1 or 8, and here we have to also provide 8. Yes, you can easily understand they are shared. So the portion for this single cube is just a part of it. So although we can find 8 silicon atoms in this drawing, but real contribution is just 1 because 8 times its weighting factor. So we will have just a number 1. Then think about this guy. Face center points. So we can also find 6 silicon atoms. They are found 6 times. However, each face-centered atom is not fully occupied by this cube. If we consider certain atom located at the face, and face is just a plane generated by meeting 2 cubes. So this one is also shared by 2 cubes. So the weighting factor should be just a half. So 6 times a half will give you just number 3. Oh, so the answer is each face-centered cubic, it has only not 14 atoms, but in reality it has the stocks or share like 4 atoms. Okay, and since diamond structure is just a copy and pasted version of our face-centered cubic, so overall how many silicon atoms in a given volume of cube, then the answer should be 8 atoms. So finally, if we calculate the answer of homework problem 1, then we have to write down this way. 8 atoms are found in a volume of a small cube whose length or whose side length is given by A, and here A is 0.543 nanometer. When you calculate it, then you will find that the answer is corresponding to 5 times 10 to the 22 per cubic centimeter. Okay, so Mr. Kim, so are you with me? And our all other students, are you with me about my explanation? So the answer should be in this way. So please feel feel free to ask me question. So okay, so then now think about this one. So thank you, Mr. Kim, for asking me this question, and that will be quite helpful to our entire students set, I hope. And let's go to our main discussion. Okay, so now we understand there are many silicon atoms. This number 5 times 10 to the 22 is the number of silicon atoms. Then my question is, how many electrons are there? If we just consider the number of electrons instead of number of silicon atoms, then we have to consider the atomic number of silicon. Of course, silicon has number 14. It means that if we consider the number of electrons inside this 1 centimeter, 1 centimeter, 1 centimeter cube of silicon, then we will have just 7 times 10 to the 23 per cubic centimeter. That will be what? That will be the entire number of available electrons. So there are 5 times 10 to the 22 atomic cores, and each atomic core brings 14 electrons. So the number of entire electrons are given by this guy. But now think about our homework number, homework problem 2. What was it? When you remember the homework problem number 2, the problem was, please search the number of electrons which can contribute to our current conduction mechanism. So the number was at 300 Kelvin, the number was what? Around 1.10 to the 10 per cubic centimeter. So that will be the answer, and you don't have to calculate it, just to find it from literature. Then now you can realize that there is really a huge difference between these numbers. There are really large number of electrons in silicon crystal structure. However, among them, the one which can contribute to current conduction is just really negligible portion. So what is the difference, or what is the ratio between them? The ratio is given by 7 times 13, who it is corresponding to 70 trillion, not billion, but trillion, 70 trillion difference between the number of total electrons and number of electrons which can contribute to current conduction. So why we have such a drastic difference between these two numbers? That will be in the course of our main lecture. So think about this one. So now we understand. Now we understand. In order to visualize our silicon structure, atomic structure, we have to draw a cube, and if we consider a point located at origin, then what will be the surrounding or neighboring points? Of course, you can say that oh, there is a certain point here, here, and here. However, their distance is given by A. A. A is 0.5, around 0.5 nanometer. That is really short, but you can find even closer neighbor, or even nearer neighbors. For example, think about this guy. The one placed in the face center. Oh, then how far is it? It is half and half along this way. So the distance will be given by simply for this face-centered guy, we will have to we will have square root 2 divided by 2. Okay, you know it quite well. So this is given by just yes, this number, and compared with our distance between these corner points, certainly this one is shorter. So this one is good. They are more closer. So our closest one is located in face-centered one. But no, that is not the case. If we consider other one, we will realize it that the nearest neighbor is not the face-centered one. What is it? The face-centered diamond structure has a copy generated from a face-centered cubic. So if we have a silicon atom located at the origin, then we have a pair which is located in quarter A and quarter A and quarter A. Then what is the distance between the origin and this point? Certainly we will have, yes, so that will be the distance. Then which one is smaller? Yes, you can easily understand. This one is around just 1.7, and this one is around 1.4. So you can easily understand this one is even smaller than the distance between the origin and face-centered point. So there is a certain relationship like this. So this guy, which is generated by a pair point or a point displaced by this amount, that is the nearest neighbor point. So now you understand there is a certain point here. Its position is given by quarter A and quarter A and quarter A. That will be the nearest point, and this one becomes, this means the face-centered one is the second nearest. So if we allow to connect the nearest one, then we can consider, oh, they are nearest, and also they are nearest. Okay. Oh, sorry about that. No. Yes. Also, we can think that there will be another. Where is my? Where is my? Okay. Where is my panther? Here we have another face-centered point and another face-centered point, and these face-centered points are the nearest points of our here the point which is highlight. Okay, so everybody, are you with me? So I'm just saying that when we consider this diamond structure, it's when and also when we consider a magnified view around a certain silicon atom, then we can find that the distance between the two silicon atoms, the shortest length, is given by this one, and we will have four surrounding atoms whose distance is the shortest. And yes, that is the situation for silicon atom. And so now come back to our original question. There are a lot of electrons. Here, this guy will contribute to 14. And also this guy will contribute to 14. And each silicon atomic core will contribute to 14, 14, 14 electrons. So that's the reason why we have a humongous number shown here. But you know that at the center of our atom, there is a strongly positively charged atomic core. So here, although we have written down in this way, this guy has 14 plus and 14 plus, 14 plus, and each one has fully 14 plus charge. Here 14 means that in the unit of elementary charge and positively charged. So our electrons, these electrons is very they are difficult to escape from the influence of this atomic core. So usually we feel or we think in this way. Silicon has 14 electrons, and basically it has 10 electrons whose distance from the atomic core is shorter, and 4 electrons whose distance is larger. So simply speaking, here we have 14 plus here, and we have 10 electrons. This is 10 electrons, and there is also another 4 electrons, and they means that these 10 electrons are more tightly coupled with our silicon atomic core, and usually we don't care about them much. Okay, this guy is fully occupied by this atomic core, and only this the outermost 4 electrons are interacting with other electrons in neighboring silicon atoms. So it means that this guy, this central one, okay, I have 14 electrons, but 10 is reserved for my own use. I can contribute 4 electrons to be connected with my neighboring silicon atoms, and all of our silicon atoms say in the same way. Okay, I can contribute to 4. I can contribute to 4, 4, 4. So by collecting them all, then just neglecting these 10 core electrons, just granted. That is fully governed by the atomic core, so they do not appear in our discussion any further. Then our view now is there is certain silicon atom, and there is a silicon atom, and this one say that I can provide 4 electrons, and also this guy say I can provide 4 electrons, and we have each one. This one has 4 nearest neighbor. So from the viewpoint of this atom, this one is not a special one. There are 4 equivalent atoms, neighboring atoms. So also we have 4 electrons to be used for sharing. So I will just contribute 1 electron for this atom, and we will have 4 or 3 more. Okay, there will be 3 more, and for each of them contribute 1 electron, and also 1 electron will be contributed. And that is the same for all of our silicon, because due to symmetry, so our silicon will contribute 1 electron, and this guy will contribute 1 electron, and here and here. Then if we consider in this way, then we will realize that a pair of our silicon atom, yes, if we consider a pair of our silicon atom, then there will be 2 electrons contributed. Each of them was contributed from each silicon atomic core, and these 2 electrons will be used to connect these 2 silicon atoms. And these electrons, 2 electrons shared by 2 silicon atom is drawn as a stick here. But this is just visualization purpose, and if we have to understand there is no stick at all, but that is just visualization of 2 electrons shared by our 2 atomic cores. Okay, so this is a long way, but let me just conclude this long discussion. So if you understand up to now, then although we have a lot of electrons available to us, however, all of them are used in certain way. So if we have to say among this large number, 7 times 10 to the 22, actually 5 times 10 to the 23 per cubic centimeter, they are fully occupied or governed by each silicon atomic core. So they are called as core electrons and does not play any role in our discussion. Only there will be 2 times 10 to the 23. Still that is a quite high number, 23 per cubic centimeter, which is used for connecting 2 neighboring silicon atoms. So this one, this one, this one, this one, and this one. However, you realize that this guy, although not solely occupied by or solely governed by the single atomic core, they are shared by 2 atoms, and there is no freedom for this guy to move to allow electric current. So although their role are different, yes, their role means that its role are different, but both of them are just tightly coupled to our silicon structure, so it cannot move at all. So now if we consider the answer of our homework number homework problem number 2, then the answer is 1 times 10 to the 10 per cubic centimeter. Okay, this is compared with this total number. This is very small number, but close to 0, but it's not 0. Then why we don't have exactly 0? Why we have a small amount of electrons which can contribute? So in reality, if we go to really 0 Kelvin absolute temperature scale, then the number of electrons which can contribute to the current conduction will be really 0. This number. However, if we elevate the temperature, then the number of conduction electron will be increased. Simply means that happens like this. When we have non-zero temperature, like 300 Kelvin, 300 Kelvin is corresponding to 27 Celsius, so this is usually called as room temperature. Then some lucky electron can have among them a lucky electron can have enough energy to escape from this control of one atomic core and another atomic core. So let me just repeat again. So at 0 temperature, there is no summer energy at all. So this is a silicon, and there is between them there is a certain electron crowd, and there are 2 electrons shared by them. And at 0 temperature, there is no summer agitation, so there is no chance for this electron to escape from this position. However, if we elevate the temperature to our room temperature, then really lucky guys can escape from this how can I say, confinement, and it can move around the silicon crystal structure. So I wanted to stress that the ratio between the total number of electrons and available conduction electrons, that is really large number, and even when we consider just the outermost one, which is shared by 2 silicon atoms, that number was 2 times 10 to the 23 per cubic centimeter. When we neglect the core electrons, which is fully occupied by our silicon, still we have a lot of electrons just occupying the stick between 2 balls. That ball means that here atomic cores, and the ratio is really impressive. The ratio is still given by 2 times 10 to the 13. It means that among 2 times 10 to the 13, 20 trillion electrons, only one single electron can have two chance escape this chain, and that lucky guy can go to the, the higher level, then it can contribute to our current conduction. So when we say in this course, from now on, usually when we say electrons, then we don't care about this entire electrons. Usually this one is not treated as electron. Of course they are electrons. However, in our purpose, current conduction, they do not contribute, so we just neglect it. And how about this guy? Even for this more narrowed scoped one, but they do not contribute to our current conduction, so we don't care about that. When you say electrons in this course, the electrons is the one really contribute to our, how can I say, in our current conduction. And its number, even at the room temperature, our world, our usual atmosphere, still the number is quite small, 10 to the 10 per cubic centimeter. So if we are using the silicon in its purest, its ideal situation, then there will be really a small number of electrons which can contribute to the electrical conduction. So in its sense, silicon is not good for current conduction. Well, this material does not conduct at all. So I got a silicon wafer and try to make a current conduction, but no current flows. That is the ideal case. Okay, of course, ideal. I will explain later why that is ideal. Okay, so that was a long story initiated by Mr. Kim's question, but I think that is good for our discussion. We have covered the main contents of our lecture course, and I'm quite happy with this one. So now we feel that this number is so small, so it is not good for current conduction. And by the way, do you have any question about my explanation up to now? Then please let me know so I can repeat again or answer your question. So do you guys have any question? Then I want to ask all of you, our students, that leave your message that you don't have any further question. Then I can move to our next discussion. Okay, please. Okay, thank you, our students. So, okay, no question from our students. And how about other students? So please leave your message. Okay, thank you. Okay, so I wanted to ask all of our students to leave your message. And once again, if you have any question during my explanation, then please interrupt me anytime. Then now you understand. Yes, if we consider silicon wafer once again, so this part is too highly resistive. The main reason why we have too highly resistible substrate is, yes, this part is more close to the purest state of a silicon crystal. So this one is close to pure silicon. So number of available electrons here once again, so electrons is corresponding to the electrons which can contribute to the current conduction is really small. So our uh, goal to have less resistible region nearby this top surface can be introduced by introduces something. I mean that here, if we increase the conductivity of our silicon material or reduce the resistivity of our silicon material, then we have to introduce number of electrons should be increased. So how can we intentionally increase the number of electrons? Of course, the first thing we can think is, or we can say is, okay, this number of electrons is really related with the temperature. So if we have zero temperature, there is no conduction electrons. But when we heat it up and up to 300 Kelvin, then although not that high, but there is a certain amount of electrons. Why don't you working with elevated temperature instead of 300 Kelvin? Let's try to use it, for example, 350 or 400. Yes, of course we can try it, but if we try it, then that will be too hot. So we are living with this, usual atmosphere, and in order to use certain electronics, we cannot elevate the temperature. So therefore, elevating temperature cannot be a reasonable way to increase the number of electrons. And there is also another way to increase the number of electrons. What is it? It is just illuminating it. So we can send photons on the surface region. Then yes, this silicon will have excessive electrons. So that electrons will be so photo-generated electrons will increase the number of available electrons which can be used for current conduction. But point is, then who can provide the photons? Oh, can we just use it only for daytime or just under the light? It's not that good, and we cannot control the number of photons precisely. So yes, sometimes this photo-generated electrons is really important for certain applications like a solar cell or CMOS image sensor. But if we consider pure electronics, not related with the photons, then it cannot be a reasonable way to generate more electrons. Then what is the way to increase the number of electrons which can contribute to our system? I think that most of you already know the answer. The answer is to introduce certain impurity atoms. So, yes, write it this way. Impurity atoms. Introduction of impurity atoms will solve this problem. So, impurity atoms means that what is the impurity? It really depends on the case. For example, in this silicon wafer, silicon is the host material. And for example, phosphorus, boron, or arsenic, they can be regarded as, impurity atoms. However, if we go to the other material system, for example, think about this guy, gallium arsenide. You have heard about it, maybe. So this is another silicon, another semiconductor material, which is made of two different atoms. Usually that is called as a compound semiconductor. And in this case, silicon is a representative impurity atom. So which one is the impurity and which one is the host? It really depends on the situation. So if something is dominant, then all the others are regarded as impurity. So since we are talking about silicon, so silicon is treated as a host material. So excessive silicon is not an impurity at all. However, if we introduce other atoms, then since this is non-silicon, they are treated as impurity. So now you can understand the way of say this is impurity and this is not. Then I wanted to say, for example, hydrogen, is it impurity? Oxygen, is it impurity? Yes, the atom, except for silicon, all of them are act as an impurity. That is true. If we are, there is only all silicon atoms, and the one which is not a silicon atom should be regarded as, all of them, or for example, iron, blah blah blah. All of them should be regarded as impurity. However, there is a clear distinction between all other atoms or elements and the one shown here. Yes, so we have many different elements in our periodic table, and in our discussion only silicon is treated as host. Therefore, in love sense, all of them are impurities. They are all impurities. However, when we say impurity, but in a narrow sense, we just treat this guy. So why we treat them only them as a representative impurity atoms? That will be explained in the next session on Monday. Okay, so we have still homework number 5. I will post them quite short, short time. And yes, the time is up. And if you have any question to me, then please send me an email. Then I will happily answer to your question. Okay, so finally, do you have any question about our story? So today, our main discussion was the large number of electrons in our silicon, but only extremely small portion of electrons can be used in current conduction because that was generated by thermal excitation. So even at room temperature 300 Kelvin, the amount of electrons which is available to us is too small, 10 to the 10 per cubic centimeter. That is not sufficient for our purpose. So we need other means, and we have tested other means like elevating temperature, not practical. So adding photons, yes, however that is not practical for our major application. So we are now talking about impurity, adding more impurities, and the discussion will be continued on Wednesday. Okay, if you don't have any further question, then I want to wrap up today's lecture and see you Wednesday. Bye.